And our next speaker is Alexander Cox from the University of Bath. Will be speaking to us about a measure-valued HJB perspective on Bayesian optimal adaptive control.
So yeah, so just to say that, yeah, there's lots of sort of similarities with Yu's very nice talk just now, and in particular, some of the concepts and sort of issues that came up just now are going to come up in this, or are really going to be the content of the talk. So again, thanks to you for a very nice talk, because actually a lot of these concepts have really just been introduced in this particular example. So broadly, I want to think about quickest detection, or well, a class of the problems that I sort of want to think about, and particularly from the optimal stopping perspective, are sort of what you might call quickest detection problems. So very much as you just sort of said, right, the sort of thing that you might think about here is you have some signal process Y, and driving the drift of that signal process is some unknown object rho. And part of the problem, so in Yu's case, this was sort of the qualities of the candidate you might be looking at. So you don't know these, but you can infer them by observing some stochastic process. W here is unseen. You just see the process Y. So the drift of this process is somehow capturing information about the quality of the candidate, or more generally, this rho you might want to observe. So one class of these are the quickest detection problems, and there you might be, there's an unknown time at which the drift of your process changes, and you want to stop as close to that time as possible. And the sort of typical problem might be these sorts of things where you penalize early stopping, and you want to sort of maximize or minimize, sorry, okay, that should be an inf over Tor, shouldn't it? Want to minimize the sort of delay past the time rho that I actually choose to stop. And here the key thing is somehow that my stopping time Tor has to be adapted to the filtration of this Y process. So I'm sort of using the observed process to sort of learn information about Y. Okay, and again, we saw this in Yu's talk. One of the critical objects in all these sorts of things is like our posterior belief about the value of some hidden parameter. So in quickest detection problems, this might be the sort of hidden, sorry, that should be rho. Okay, I've clearly not looked at my slides carefully enough. So that's the probability that this hidden signal rho is in some set A, conditional on the observed information filtration. And in Yu's context, this was sort of the quality of the candidate, which we learned by sort of observing the drift of these processes. And so again, we get some posterior belief process psi, which is sort of about the hidden information that we want to learn about. And so if you looked at what Yu was trying to do in her talk, or she managed to do in her talk, what you sort of try and often do in these problems is you play around with using the facts that what you know about the problem, and essentially you try and take this posterior measure as your sort of state variable, and you reformulate your optimal stopping problem in terms of this state variable, and that gives you your stopping problem, right? So you can reformulate the stopping problem in terms of this posterior probability. In Yu's case, the sort of set A, or the candidate values, was only where you have two possible values. So you can try and reformulate psi as your state variable. And so now you can formulate a one-dimensional, potentially optimal stopping problem in terms of some sort of posterior probability. Okay, and so there's a wide variety of these types of problems. And in all of these sorts of games, you're basically, or these problems, you're basically trying to play this game of reformulating your problem of the posterior distribution and trying to understand what the process that's driving that distribution is, and potentially, if you want to solve an optimal stopping problem, trying to formulate your problems in terms of the dynamics of this psi process. So what do I want to think about in this context? So these problems are well studied. I want to sort of think about what happens if you introduce other elements of control. Okay, so what could you have in this problem? Well, maybe I can control how I measure things. So maybe instead of just observing this H of rho, I have some box, and I can increase the sort of increase how, the signal strength. So maybe I can reduce the value of sigma. Okay, so then I have a more signal and less noise, so it's easier for me to detect the signal. Okay, and maybe there's some cost to that, so maybe I have to minimize the cost. Okay, so I could play around with having some control over the measurements, or the way I measure them. Maybe the way I learn, oh, sorry, going the wrong way. The signal I receive, maybe it's more complicated. So this is quite a nice process. Maybe I just smear this out slightly. Maybe I can see a little bit into the future, or maybe I start getting some signal slightly ahead of this time rho. Okay, so maybe there's a fixed time rho where something's going to happen, but I start seeing a little bit ahead of just before it's happening. I get some smaller signal. So this H is not just this nice step function, but you can look a little bit at, or you sort of get some identification of things that are about to happen. Or maybe actually I get some control in here as well. And maybe the reward I want to look at could depend not just on, I'm going the wrong way again. So this depends only on the choice of the actual time and my choice of the stopping time. Okay, but maybe actually what I want to do is, if I'm in this Bayesian context, I want to try and maybe how certain I am could also be part of my reward. So not just, so maybe I want to sort of give an extra reward or sort of prefer situations where I stop and I'm actually really certain about the answer. Okay, so you could imagine our reward function depending not just on this average, but also on elements of our posterior belief. Okay, so it would depend on elements of this thing here. Okay, so you could imagine, I can formulate all these things, right? The question is, how can I solve anything, right? So these are all ways in which this problem can become more complex. And so you can ask, actually, there's a much bigger class of problems in which sort of capture all of these features. An example of a more general type of problem, which is now very much a control problem, but has very common features with some of the stopping problems we talked about, or we just saw it in use case, you could think of as being Bayesian search. Okay, so I have some unknown location, right, a big box, and I know that there's some thing I can listen out for that's somewhere in this box. Okay, you can think of this, so people have sort of talked about these in the context of, you have a plane crash in a sort of an ocean, right? You send out search parties looking for these things, you're looking for some signal, right? So what do I know? Well, I probably have some belief about where it's crashed, but what you then have to do is you have to send out boats, right? And you might say, well, I'm going to sit my boat here, I'm going to listen for some sort of signal, and it's going to be easier for me to detect that signal the closer I am to X. Okay, so how might I try and detect this? Well, you'd probably want to do some sort of, well, I'd circle around, I'd listen to different things, and you'd look for where that signal is the largest. Okay, so now you can think about this in this form up here. So my signal Y is the same thing, but now the strength of my signal depends on the unknown position X and also the location where I am at a given time T. Okay, so now I need to choose a position, a track, a location, according to some condition or some sort of criteria, and I want to try and essentially maximize the probability that, okay, at some point I'm going to stop, I have to do a sort of a search at some point, and I want to try and make sure, so what you could say is, okay, I run this up to some time, someone tells me I have to stop, I have to sort of send out to the proper search party. So I choose a location at this point, and now I'm going to search, and I'm going to search in some ball of radius r around this point. And what do I want to do? Well, I want to maximize the probability that I catch or I find the thing I'm looking for. So now what am I going to do? Well, I sort of, okay, if I have an independent exponential stopping time, for example, or a random So the time at which I stop is maybe some independent time. What's the criteria? Well, when I stop, I'm going to look at my posterior distribution, and I'm going to choose the point Y, where, okay, I know I can search in some ball of radius R around that point. I want to choose the point Y, which maximizes the posterior probability that I'm in that ball. Right? So that's quite a complicated object. If you think about this at the level of operations on measures, right? This is a very complicated object, right? Because, okay, I could have, so, the sort of measure I could see, right, is something which looks something like this. And now, okay, I could choose a ball here, but maybe, okay, there's a high probability of being at this point, but a low probability of being around it. Whereas if I take a ball here, because my density function is high on the whole of that ball, maybe I'm better off not going for the point where my density is largest, but going for a point where, okay, I have quite a lot of density in a sort of region. Okay, so this is quite a complicated operation on measures, right? But you could think of this as a reasonable choice of a reward function in these sorts of Bayesian search problems. Okay, so this is a very complicated choice of reward function, but in the general class of these problems, you could imagine this as being a potential sort of choice of how you might choose, or what criteria you might choose to optimize these problems. Okay, so now I have quite a general class of control problems. Okay, and the question is, well, okay, what can I do? Can I even formulate these problems correctly? So say a little bit about the literature. So we've sort of been doing some work on these problems, and so within the optimal stopping literature, very nice talk by you, we've just sort of seen. So there's sort of problems. Okay, I've gone back to the sort of sequential detection, quickest detection problems, and these have a very long history in optimal stopping. Okay, so going back to sort of Wood and Shiraev and various people have worked on these for a long problem, with elements of filtering and learning. So this is a paper by Eric, Ioannis Karatsas and Veshinivius for quite recently, and also the paper we just heard about, so Ekstrom and Wang. So both of these have a sort of element of this filtering and control and stopping optionality. There's also quite a big literature in the stochastic control on stochastic control under partial information. So here you have so it's different to our context in essentially this X can be a stochastic process, and potentially you can control X. Okay, so there's very close connections, but it is slightly different because we have a fixed signal, but we can control how you listen to that signal. So we can essentially control not the dynamics of some hidden signal, but we can control how you learn about that hidden signal. Okay, and so from our perspective, there's important technical reasons to do that, but also differences in terms of the sort of problems you consider. But there is a big literature on these sort of stochastic control problems under partial information, most of which is really doesn't quite cover the case we want to think about. Okay, most of the time, the control really only comes into how this X process behaves. Okay, and then, but yeah, so there's very little on the explicit control of the filtration. There's one recent paper which really inspired us, which is by Cohen, Nockenhauer, and Merkel. And there they really do look at a very similar problem to us, but in a much less complicated setting. So they're very much reducing things to a finite set of control problems, but where, okay, they have a little bit more than just a one-dimensional thing. They have a sort of a variance of the measure as well, and they use various tricks to be able to reformulate that. Okay, so our approach is going to be very much inspired by them, but also the tools we have at our disposal allow us to do quite a lot more general results. So we can write down quite a general control problem, but I want to sort of, and this was partly why I asked you this question, there's a real sort of issue here with how you define admissible controls. Because we choose a control, and that has to be adapted to our filtration, but the filtration is the information we receive, and that is going to depend on our control. So there's a sort of circular issue here, where you want to try, well, how you define these controls is non-trivial. Okay, so again, we're going to follow really the Cohen paper. And the approach we take here is we start by defining quite a broad set of controls. Okay, so we have an action set U, and our controls initially are just going to be controls which are progressively measurable with respect to the sort of some very sort of high level probability space. Okay, so we fix a probability space. We just need progressively measurable controls with respect to that control space. And then we define our observation process. And then, okay, then we take our filtration. And so these are the pre-admissible controls. Okay, we use these pre-admissible controls to define our signal process. And then, well, then we sort of go back and say, I need to have chosen a control which, when I do this, actually is also progressively remeasurable with respect to the filtration I now observe. Okay, and so this whole process itself, right, I can't tell you if I give you an arbitrary control at the start, am I going to end up in this set, right? There's no nice thing, right? It's a sort of suck it and see type thing. If I give you a control, you might end up in the set, but a priori, there's no reason to know I end up back in this set. Okay, but it gives us a way of defining a set of admissible controls. Okay, it allows us to turn all the other handles. So we can do this and we can define a control problem. Okay, but the problem is all of the classical tools you have are somehow not really readily accessible. Okay, but we can do this. We can define a control problem. We can define our posterior measure. And we can think of that as a state variable for a control problem. We can define some cost functional. So now I have a J, which is, well, defined on some weird set that I don't really have much control over. But I can talk about a cost functional, and I want to optimize this cost functional. So this is a sort of the natural problem you would try and formulate, but it's very hard to do anything because I just don't have any nice control over or don't have any nice sort of handle on the set of controls. Okay, so this is like the sort of, okay, if I try to work out what someone is trying to solve, okay, they have some information, right? They're choosing something, this is where I'd end up. Okay, but as we saw in Yu's talk, this actually isn't the problem we're going to try and solve mathematically. What we're actually going to do, so in the literature this is called something like a separation principle, is to try and reformulate this nasty problem in terms of what is the dynamics of this state variable? Can we formulate the dynamics of that state variable as some underlying process and then write down the corresponding control problem corresponding to that set of possible dynamics? Okay, and so particularly in the stochastic control under partial information literature, these are called separated and non-separated problems. And there's a question of how you end up in, how you go from one to the other. So there is a literature, and essentially in the sort of stochastic control under partial information literature, you tend to use some notion of wide sense controls, which are adapted to a fixed filtration, and then try and show that actually these the class of wide sense controls and the class of actual controls you might see are somehow don't change the problem, and then you can sort of turn the handle and get the fact that these two problems are the same. But we're going to take a slightly different approach, which is sort of inspired by this Cohen paper. Okay, so first of all, what is the right separated problem here? Okay, we can write down, essentially this is classical filtering. Just there's some nasty measure valued SDEs here, right? So this is our stochastic differential. So it's a stochastic differential equation for the measure valued posterior process, right? And I sort of write it down by applying my measure to a test function. And I can say, if I look at that test function, what the dynamics are, okay, for a given signal process. And then you can write this, so you can write it down with this yu minus psi. And then the standard trick in the filtering literature is this, to look at the innovations process, and under the right filtration, or so this is adapted to the filtration yu, and this process itself, right? So notice you have this difference between H and what I think H is under my posterior measure, right, is actually a YU Brownian motion. So I can rewrite the psi dynamics as this nice SDE. Okay, or no, I say nice. I mean it's a nasty object, but it's at least something I can sort of think of as having, right. This is just a Brownian motion, right? There's a nice dynamics in terms of my current state, the choice of my control, and some test function. So what is this object? Well, this is where we've come in. So we've actually looked at these sorts of objects. So this is what I can call an MVM, okay, a probability valued, measure valued martingale, because the key property here is somehow that if I apply it to a test function, I have no drift term, right? If I look at the measure on any set, that measure will be a martingale because we're looking at the posterior measure of a fixed signal. Okay, all that we're changing is the information. So these sorts of things have been studied. So you can go back to some papers by Yor, for example, and actually you can write the dynamics of these MVMs also quite nicely in terms of a covariance, where you have the covariance of rho, which is our control, with a test function phi under the psi process. Okay, so so we started with this really nasty problem, which is somehow the real problem. And what we've done is we've transformed it into a nice problem, which is about where we try and control the state, the sort of the posterior dynamic or the posterior measure. Okay, and this is what Yu was doing as well when she wrote everything in terms of the likelihood of a given state, right? In Yu's context, the probability measure was essentially a 0, 1. We had two states, right? The good and the bad states. So a probability measure on two states can be written as one number, right? It's the probability of being in one of those states. And that probability, if you look under the right measure, is a martingale. Okay, so we have exactly the same sort of setting here, except now our dynamics, because we're in this more abstract world, are more complicated, right? We have a bigger class of controls. We can do more. Yeah, but we still have this problem of how do I write down a well-formulated problem? And so we can introduce a notion of weak solution, which is essentially I'm allowed to write down anything I like. Okay, so I actually construct everything at once. So I construct a probability space, a Brownian motion on that probability space, and a measure valued martingale, a control, all of these things I give you, but such that the dynamics is controlled, and that gives us a nice way of constructing these things. Right? I construct everything, so therefore, well, I need this progressively measurable condition on my control, but automatically when I construct it in this way, I get a control that is of the right form that allows me to sort of ignore all the issues I've talked about with the filtrations. And then we can hit this with heavy machinery, right? So I mean, you can write down, okay, there's nothing complicated here in the sense that this is a very classical HJB. We have a single state variable. You can control this state variable. You write down the HJB equation, right? You get something, right? You have to, right? The problem is so this is our HJB equation. The difficulty somehow is here. There's a measure valued state. I need to tell you well, I'm not going to tell you what it is, but you need to define somehow the notion of the second derivative of a measure valued function, sorry, of a function which has a measure as its input. Okay, how do I take a second derivative? Well, it turns out you can do this. There's a sort of various notions of derivatives. So in particular, in this previous work, we did this. It's very similar to things you'll find if you look in the mean field games literature. And so in this paper, what we're able to do is basically define all the heavy machinery to say, well, the value function for our separated problem is a viscosity solution of an appropriate equation. Okay, and so I'm sort of running out of time, but so that gives us a value for a problem we've sort of created to look a lot like the problem we actually want to solve. Now the question is, are the two problems actually the same, right? Or have I, by transferring myself into the nice world, have I lost something? Okay, and so the answer to that is where we have to do some work. So we have to try and come up with another notion of solution which looks a lot more like the first case. Now, there is one type of control in this new world that you can construct that sort of you can avoid all these problems of circularity, right? Because if I just have essentially I do it in a discrete way. So I choose an initial control, let my process evolve, stop it at say a fixed time. Now I know my filtration. I can choose a new control which is adapted to the given filtration and set myself off holding my control constant and then keep going. Right? This is well, you can easily check that this is well defined in terms of the type of controls you want to look at. Okay, so you can approximate your problem by doing this, right? So all this is a bunch of details, but essentially these controls, right? We take some dyadic intervals and you just do this on a finer and finer partition using this process. Okay, so we can define now a value where I fix a partition just as the control corresponding to the fixed width. And we can take limits because these are decreasing, so we get the limiting value function. Okay, and so now the question is, are these things the same? And it turns out, okay, they are the same. And in fact, because I know this weak solution is better than the sort of true value of the non-separated problem, which in turn is better than this V plus, the limit of these approximate solutions, right? The true value is sandwiched between these two. Okay, so by showing they're equal, we have the fact that they're the same function. So we can do this and we can characterize the solution. So the proof, I think I've got to have time to talk about it, but goes through using the viscosity theory and so on. So we can use viscosity theory to show, in particular, this function and this function are solutions or super solutions in viscosity sense. And so therefore, there's an inequality and so on. And then also we can use this to get a sort of an epsilon optimal control, right, coming from these approximate problems. Okay, so the solution is, or the sketch of the proof goes via the fact that we already know a lot of viscosity theory about these types of solutions, and we're able to sort of verify everything. We need to prove a sort of stability result for these MBM SDEs, but we can do all that and we can go through and we can prove actually these things are the same. So in the last few minutes, I wanted to try and connect back to an optimal stopping problem. So where do we come from? We come from, or one of the reasons why I'm looking at this is because I have an old paper now with Sigrid Kalblad from this one, where we sort of looked at the Skorohod embedding problem, which is, okay, I have a Brownian motion B, I give you a distribution mu, and I want to find a stopping time that embeds that distribution. So when I stop my Brownian motion, I give you a distribution mu. Okay, and in fact, you want to do it in a way that optimizes some function f of maybe the path. So it could be the stopping time, or well, it's not stopping time because that would be fixed, but maybe the square of the stopping time. It could be the maximum of the process B. Okay, all these sorts of things have different examples. But it turns out that you can interpret these things as a sort of, as an MVM type problem. So if I look at the MVM, so psi is a measure valued process, and I start it at where I want to end up here. And now I choose some way of letting it evolve. That there's basically a correspondence between dynamics of MVMs and choices of stopping time to solve the Skorohod embedding problem. So there's a sort of, so in this paper, what we sort of say is, well, I can reformulate the optimal Skorohod embedding problem using dynamic programming as a sort of control problem. And the control is how I control these MVMs. So we can exploit this because what's the, right, so you've probably, I showed you an HJB equation, right? It's a complicated HJB equation. You could have said, okay, are there any, or how do I find solutions to this object, right? And that's a very valid question, right? We can write down a small number, but in general, this is a hideous equation on a measure value space, right? So what's the chance of us solving it? Well, it turns out, there's a question mark here because I haven't sort of written the details, but essentially via all these connections, what we know is if I take a particular construction that I know to be optimal, so for example, the root embedding, right? So this is chosen. So I take a time-space domain. I take a Brownian motion and I just run it to the exit of some time-space domain. And this domain has to be sort of closed to the right. I can always find a set in this way that gives me a solution for a given mu. Okay, and so I can actually use that to construct solutions in very specific cases for these HJB equations. Okay, so if I give you a very specific choice of an embedding equation, or sorry, of a set of controls and an objective function, right? The optimal value corresponds to the expected value of the exit of this, of the exit time squared. Okay, and in fact, going back to optimal stopping problems as well, it's also known that I can reformulate this in terms of an optimal stopping problem, right? There is some lambda, right, sort of penalty function, such that the expected value of tau squared is equal to the solution of an optimal stopping problem for some, okay, the tau squared is the same, right? The key thing is I need to choose lambda mu in a particular way, okay, which will depend on the choice of mu I need. But there's a formulation of this in terms of the solution to an optimal stopping problem. So I can write the value function as a sort of unified collection of values of optimal stopping problems. Okay, and so now, is there some way we can exploit this, right? So this is a very specific example. Does this tell us something about maybe local behaviors of solutions to these HJB equations? Can we always formulate them in terms of these optimal stopping connections, for example? Okay, is there something fundamental here about how these optimal this relationship, does it give us something deeper about these sorts of MVM type HJB equations? Okay, so that's where I want to finish. I mean, there's a summary there, but I think I'm a bit over time. So, yeah, I think that. But I think for this conference, I think that the really interesting question is there a connection somehow between these very sort of abstract class of MVM or HJB equations and representing these solutions in terms of solutions to particular well-chosen optimal stopping problems? But okay, I'll finish there.